Hi guys, Dr. B here. This is topics 4.3 and 4.4, representation of reactions and physical chemical changes. For topic 4.3, the objective is to be able to represent a given chemical reaction or physical process with a consistent particulate model. So the important things to think about is the relative location of your particles. So for example, when you look at a reaction, let's say it is HGO, solid produces 2Hg liquid plus O2 gas. So you have the number of moles of each reactant or product, inner product. You have the physical state. You have how many things are associated with each other. When you see the state of matter, remember how solid, liquid, and gas particles are supposed to look. If it's an aqueous solution, sometimes you only show the solute particles, the ions. Maybe you should they may tell you to put in the water as well. If the molecule will ionize or not. So like if it's a molecular, so like C6H12O6 will not ionize, but if it's NaCl, that ionic compound will ionize. So when I said molecule, I misspoke, I apologize. So like we said, solid, liquid, gas, how the particles are arranged. The movement of particles is all review. Some context clues may be if it's a surface or interstices of an alloy. The precipitate, a solid particles should be at the bottom once they have settled. A few may remain throughout. Interfaces where two substances meet, water and air. The amount, make sure you have the proper amount of atoms present for each formula. Use the relative amounts of atoms when a given quantity mole concentration is given to you. Observe the law of conservation of mass. Keep the same number of each type of atom present before and after, just rearrange them correctly. The correct species, meaning shapes, circles, squares, whatever, shades to identify different atoms or ions. Use a key or the elemental symbol from the periodic table. Show the charges if you need to, and then outline appropriately. Use appropriate sizing. If this is atoms of the same element should be the same size. If it's different element, they should try to follow atomic ionic trends on a periodic table. The pictures below show the process, oh my god, I can't talk right now. The pictures below show the process of H2 and Br2 reacting. It does not go to completion, however, it reaches a state of equilibrium. And you can tell because not all of it is reacted through, meaning not all of it has broken up. So what are the kind of silly. What are the formulas for the reactants? It's going to be H2 and Br2. What's the formula of the product? We can see that if we start looking at picture 2, 3, and 4, the product is right here where it's kind of hovering. So this would be HBr. What is the balanced equation? Include states of matter. So you have H2, it's like it's a gas to me, plus Br2 is a gas. Get it? And then it makes HBr. If you look at the products, how they're interacting, it is not a solid liquid, so it's a gas. And make sure when you balance, you put the 2 in the front of the HBr. What is the difference between picture 2 and 3? More HBr was formed. What do you notice about the total number of atoms of each element in all the pictures? What concept does it represent? The number of each atom is consistent throughout. This demonstrates the law of conservation of mass. Ugly. Mass. Draw the representation of 4 molecules of hydrogen and 4 molecules of oxygen completely react to form water. So water can be water vapor, it it can be a liquid if you want. So you have to remember though, hydrogen and oxygen, when you say a molecule of hydrogen, that implies that it is two H's bond together, because hydrogen and oxygen are examples of diatomic elements. So let's say that a hydrogen molecule is going to be like this. Let's put together. O2, it's going to be a little bit bigger. So if you put in your left to right, so on the left I'm going to put 4 of my H2s and also 4 of my O2s. You can barely tell there's a difference. Okay. So you have to make sure that based on what you have on the left is equal to the same number of hydrogens, whatever, like the same number of hydrogens on the left and right hand side. So for example, so this is my reactants, these are my products. If you notice, I probably will have maybe 4 water molecules, because for every 2 H's I have 1 O. And it looks like it may be kind of a weird situation where you have, let's see, if I use, so don't do this on your paper, but I'm trying to show you how this would work out. So for every H, so if I were to close out, like get rid of this one, I get rid of 1 O. Oops, wrong one. So the only part that I need you to write are the products, not the crossing out. But the crossing out shows you how much of each I'm going to have left. So if this is gone, then this will be gone. If this H2 is gone, this O is gone. If this is gone, then this is gone. And I have 2 O2s left over. That's what I mean. So the crossing out, don't do that, but I'm trying to show you the process by which you figure out how much you have of each element. Topic 4.4, physical and chemical changes. The objective is to be able to explain the relationship between macroscopic characteristics and bond interactions for chemical and physical processes. A physical process occurs when a substance undergoes a change in properties, but not a change in composition, such as a phase change or mixture separation. You have H2O, solid versus liquid. So when water melts, the chemical makeup does not change. The intramolecular bonds or forces stay the same. It's just that the intermolecular forces, they're the ones that are broken. Intra stays the same because it's within the molecule. Inter is between. A physical process occurs when a substance is transferred into a new substance with a different composition. During a chemical process, bonds are broken formed. Examples would include chemical reactions where 2 elements bond together to form a compound. The compound is broken down into elements or new compounds, or a neutralization reaction that produces a product as water. So here is a chemical process. The filtration that you saw earlier, that was actually an example of a physical process. So chemical process is shown here. So the picture, so you see a chemical change. Notice that the bonds are separated and that new bonds are forming. The intramolecular forces, covalent bonds are broken and reformed. So label each process below as a physical or chemical, as well the type of forces that are broken or formed during the process. So look at these and we'll go over those in a little bit. So for the first one, we have CH3OH liquid, and then it forms a gas, or becomes a gas. So this is a physical change, and the types of forces that are broken, intermolecular forces. Next you have iron plus O2 makes iron 3 oxide. So two things are coming together. Phase changes involved, not phase changes, but like solid and gas together becomes a solid. So this is a chemical change, and intramolecular forces are broken. So if you look at the next one, it's the same thing. So, which actually should be 3. So this is also a chemical, intramolecular. Here you have solid to gas for CO2, so this is physical. And then intermolecular forces are broken, INTER. So draw and label a particle diagram of liquid HCl becoming a gas. Explain how this is considered a physical versus chemical process. So it tells you that it's just going from liquid to gas. So, for example, if I have, let's make a key. If I want to say this green, it's going to be my chlorine. This blue, smaller blue, will be my hydrogen. So we know that H is less electronegative than chlorine, so that creates a dipole So we have a slightly positive, slightly negative. So right now here, this is a covalent bond. This is an intramolecular force. So you know, it's associated, we kind of know this already, but it's associating with another one. So this is the, right here, this is the intermolecular force. So what's happening going from liquid to a gas, and it's the same substance? So we know that's a physical process. So we have our liquid. It's going to associate with another one. Pretty somewhat close, I guess. There's still some space because of the dipole interaction. Oh, sorry about that. So this is liquid to gas. Now they should be a little bit closer, but this is where like the dipole interaction is here, here, etc. Maybe even here as well. So then it goes from that to something like this. But further apart. So this is a physical process because the intramolecular forces are still present, the covalent bonding within the molecule, but the intermolecular forces are being broken because we're getting further apart. All right, that's it for now. Let me know if you have any questions. Thanks, bye.